Hello everyone, myself Dr. Santime Kundu. I welcome you all to this lecture of soft computing techniques. This is the third lecture of module 5. So, in module 5, we have already covered the concepts of population diversity and selection pressures, exploration and exploitations, and some technique of selection methods. In this lecture, we'll try to understand some concept of crossover techniques. So crossover techniques in genetic algorithms are method used to combine the genetic information of two parent solutions to create offsprings. These techniques mimic the process of natural reproduction and help in exploring the solution space more effectively by combining the strengths of two individuals. The primary goal of crossover is to produce offspring that can potentially outform their parents. So there are a few crossover techniques for binary coded chromosome, also for real coded, also for real value chromosomes, and also for order permutations chromosome. So first discuss the crossover technique for binary coded in genetic algorithms. So there exist a large number of crossover. So there exist a large number of crossover schemes. Few importance, few important of these schemes are given below: single point crossover, 2 point crossover, multi-point crossover. We already discussed this. Then an uniform crossover, then half uniform crossover, shuffle crossover, matrix crossover, 3 point crossover. So this is the binary coded genetic algorithm. These crossover techniques are for binary coded genetic algorithm. So, so first we try to understand the single point crossover. So here the two parents are, so parent 1 and parent 2. These are 0 1 1 0 0 0 1 0. Next is that 1 0 1 0 1 1 0 0. So now we want to cross over after this point. Okay, so here you will get the offspring O1 as 1 0 1 is there, and the remaining portion from here 1 0 1 1 0 0. Offspring 2 you will get it 1 0, then remaining portion come from here 1 0 0 1 0. So that is offspring 1, this is offspring 2. Now 2 point crossover. 2 point crossover marks two point. So here 0 1, then this is 1 0 1 1 come from here, then this is 1 0. Similarly for 1 0, this 1 0 0 comes here, and that is 0 0. So we'll get a 2 offspring. Another is that multi-point crossover. So in case of multi-point crossover, a number of crossover points are selected along the length of the string at random. So the bits lying between alternative pairs are then swapped. So here parent 1 is 0 1 1 0 0 0 and 1 0. So here you can write parent 1 as 0 1 1 0 0 0 1 0. Parent 2 is 1 0 1 0 1 1 1 0. Suppose there are three points, so 1 0. So for offspring 1, first you will get 0 1 from here, then 1 0 from here, then 0 0 is there, then 1 0 from here. In offspring 2, so that is 1 0, then here is 1 0, then here it is 1 1, then here it 1 0. So this is alternatively changed. So that is 0 1 for this is for 1 0, this is for 0 0, this is for 1 0. So this is for offspring 1, and for offspring 2 1 0. So that is already 2 circle. So 1 0, then 1 1, then 1 0. So in this way you will get the concept of, so in this way you will get offspring by the concept of multi-point crossover. And this is that uniform crossover. So uniform crossover is more general version of the multi-point crossover. In this scheme, at each bit position of the parent string, We toss a coin to determine whether there will be a swap of the bits or not. The two bits are then swapped or remain unaltered. So here before crossover we have parent 1, that is 1 1 0 0 0 1 0 1 1 0 0 1, and parent 2 0 1 1 0 0 1 1 1 0 1 0 1. So now coin tossing, so that is 1 0 0 1 1 1 0 1 1 0 0 1. So rule is that if 0 bit then swap, otherwise no need to swap. So here it is 1 bit, so no need to swap, so that is 1 0. 0 bit, so need to swap, so that is 1 1. 0 bit need to swap, so that is 1 0. So now it is 0 1, now it is 1 0. 1 bit no swap, 1 bit no swap, 1 bit no swap, again 0 bit, so it is the 0, so it is now again 1 0, so that is 1 0. So again 0, so it is again you can write it 1 0, it is 0 0, so then no swap. So where the 0 bit we need to swap, so here we have made the swap, 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 here we have made the swap. So see here 1 1 no change, 0 0 change, 1 0 change, 1 1 1 0 no change, this is 1 0, then no change, no change, no change, then change, change, then no change. So in this way we will get a offspring by the uniform crossovers. You get it by the uniform crossover. Now uniform crossover with crossover marks. Here each gene is created in the offspring by copying the corresponding gene from one or more other parent chosen according to random binary crossover marks of the same length as the chromosome. When there is a 1 in the marks, then the gene is copied from the first print. When 0 in the marks, gene is copied from the second print. The reverse is followed to create another offspring. So here the before crossover, this is 1 0 1 1 0 1. So these are the two parents before crossover. Marks is that 1 0 0 1 1 1 0 1. So rule is that if 1 in the marks, copy from parent 1 else parent 2. So this is 1, so that is 1 is here, 0, so that is parent 1. So this 0, so that is from parent 2. 0, so that is parent 2, 1, that is parent 1, 1 parent 1, 1 parent 1, 0 parent 2, 1 parent 1. So here we will get it 1 1 1 0 0 1 1 1. Now if the rule is changed, so if it is 1, copy from the parent 2, else from parent 1. So now copy it, so this is 0, this is 1, so 0 0 1 0 1. So that is the uniform crossover with marks. Now half uniform crossover, that is HUX. So in the half uniform crossover scheme, exactly half of the non-matching bits are swapped. There no need to swap the matching bits. So calculate the Hamming distance, that is the number of different bits between the given parents. The number is then divided by 2. So the resulting number is how many of the bits they do not match between the two parents will be swapped, but probabilistically. Choose the location of these half numbers with some strategy by coin tossing and swap them. So these are the before crossover. Parent 1 is that 1 1 0 0 0 0 1 0. Parent 2 is that 1 0 0 1 1 0 1. So this is match, so that is not match, so this is that not match, here also match, this is the not match, not match. So there will be distance is 8, so that is 4. So here only 4 bits are required. So that is 1 0 1 and that 1. So here is a tossing is 1, then swap the bits, else not. So it is no need to, it's a match, so no need to change it. So 1, so 1 is there, so we need to swap it. So now it is 0 1, no need, same bit, 0, no need, so it is 0 1, so 1, then change it 1 0. So in this way we'll get offspring 1 and offspring 2. Now sample crossover. A single crossover point is selected and it divides the chromosome into 2 points called schema. In both parents, genes are shuffled in each schema. Follow some strategy. Follow some strategy for shuffling bits. Schemas are exchanged to create offsprings. So here we can swap these two. So that is parent offspring 1. So we will get it like this. 0 1, so that it swaps, will get it 0 1 like that. So similarly, if we swap 1 0, so that is also 0 1, so we can swap it to get the offspring. So that is the sample crossover. Now the thing of matrix crossover. So check some point. So that is 6 1, this is 2 3, this is 4 6, same also there. So now it is 7 2 6 9 comes from there, 2 3, so 4 2 comes from there, 4 6, so 4 7 comes from there. So that is another concept of the crossover technique. Now try to understand the 3-point crossover. In this technique, 3 parents are randomly chosen. Each bit of the first parent is compared with the bit of the second parent. If both are same, the bit is taken for the offspring. Otherwise, the bit from the third parent is taken for the offspring. So if we change the rule, we'll get another offspring. So P1, P2, P3. So as the bit are not matched, so you can take it from the third parent, 0. Which are matched, so this is 1. This is also not matched, so 1. Not matched, so 0. Not match, so 1. Match, so this is 0. Match, so this is 0. Match, so this is 1. So if we change the rule, we'll get the another offspring. So these are the crossover technique for binary coded genetic algorithm. Now crossover techniques in real coded genetic algorithm. The crossover technique for real coded are as follows, that is linear crossover, blend crossover, and binary simulated crossover. Linear crossovers. The scheme uses some linear functions of the parent chromosome to produce the offspring. Suppose P1 and P2 are two parameter values in two parents, then the corresponding offspring values in chromosome can be obtained as chromosome offspring 1, so that can be written as alpha 1 P1 plus beta 1 P2. Alpha and beta are some the constant. So that is for C1. For C2, you can write it alpha to P1 plus beta to P2 in this way. Suppose parents is 15.65, parents 2 is 18.83. Assume this thing, alpha I plus beta equal to 1. So these are the alpha 3, beta 3. So if you apply this, you will get offspring 1, offspring 2, offspring 3. By using the formula alpha 1 P1 plus beta 1 P2 for C1, alpha 2 P1 plus beta 2 P2 for C2, for C3, alpha 3 P1 plus beta 3 P2. So advantage and disadvantage, it is simple to calculate and hence faster in computations, can allow to generate a large set of offspring from two parents if only need to change the alpha and beta. Control are possible to choose a wide range of variations. Disadvantage, needs to be decided the values of alpha I and beta I. It is difficult for the users to decide the right values for alpha and beta I. If alpha and beta values are not chosen properly, the solution may stuck into a local optimum. Now, another crossover for technique for the real coded genetic algorithm. Let P1 and P2 are two parameters values in two parent chromosomes such as P1 and P2. We assume that P1 is less than P2. Then the blend crossover scheme creates a children lying in the range P1 minus alpha into P2 minus P1, P2 minus alpha into P2 minus P1, where alpha is a constant to be decided so that children's solution do not come out the range of the domain of the said parameter. Another parameter, gamma, has to identify the utilize the alpha and a random number r from 0 to 1. So we write a gamma that is equal to 1 plus 2 alpha, alpha from there, r minus alpha. So C1 is 1 minus gamma P1 plus gamma P2. C2 is 1 minus gamma P2 plus gamma P1. So let P1 equal to 15.65, P2 18.83. So C1 will get like this, and C2 you will get like this. So this is one crossover technique. So now another crossover technique is simulated binary crossover. This scheme is based on the probability distribution of generated children solution from the given parents. To spread factor alpha is used to represent the spread of the children solutions with respect to the parents as given below. So alpha is equal to C1 minus C2, P1 minus P2, take the mod of that. So three different cases may occur: alpha less than 1, so that is contracting crossover. The spread of children is less than the parents. Case 2, alpha greater than 1, expanding crossover. The spread of children is more than the parents. Case 3, alpha equal to 1, that is stationary crossover. The spread of children is same as that of the parents. So probability distribution for contracting crossover, C alpha equal to 0.5 Q plus 1 into alpha square. For expanding crossover, E alpha equal to 0.5 Q plus 1, 1 by alpha to the power Q plus 2. The following steps are used to create two children solution C1, C2 from the parents P1 and P2. Create a random number, so that is from 0 to 1. Determine the alpha such that 0 integration 0 to alpha 1 C alpha D alpha equal to R if alpha less than 0.5, E alpha D alpha if R is greater than 0.5. Using the value of alpha dash to obtain two children C1 equal to 0.5 P1 plus P2 minus alpha 1 mod of P2 minus P1. C2 is 0.5 P1 plus P2 alpha 1 mod of P2 minus P1. So example is that suppose P1 equal to 15.65, P2 is 18.83, Q equal to 2, so we'll get alpha 1 equal to 1.0772, let R is greater than 0.5. So on this case we'll get C1 equal to 15.52 and C2 equal to 18.95. Advantage is that we can generate a large number of offspring from two parents, more exploration with diverse offspring. Results are accurate and usually terminate with a global optima. Crossover techniques are independent of the length of the chromosome. Disadvantage: computationally expensive, as you have seen it, compared to binary crossover. If proper values of parameter involved in the crossover technique are not chosen, then it may lead to premature convergence with not necessarily optimum solutions. So in the conclusion, we can say that today we have learned some crossover techniques for binary coded genetic algorithm and real coded genetic algorithm. So given one question, try to solve it. Question is that P1 equal to 11100011010, P2 equal to 10011101001. So try to find offspring 1 and offspring 2 by single point crossover multiple point crossover, uniform crossover with proper assumption, half uniform crossover. You can assume proper parameter for these two crossover. So you can assume proper parameter for these crossovers. Single point you can free to use any single point, multiple point any multiple point crossover any multiple points, uniform any uh, tossing of a coin, half uniform anything you can choose it. And second is that suppose P1 equal to 10.32, P2 equal to 17.56, find offspring 1 and offspring 2 by any two crossover technique of real coded genetic algorithm. Assume necessary parameter. Assume all parameters. That is the all required parameters. So these are the references of today's class. Thank you.